going to interpret and read the graph of a function. Now I've drawn a graph here, and I haven't labeled the axes. This is the graph of f. Okay. That's what we are looking at, and so we're going to assume this is the x-axis. Now normally we would call this the y-axis, but of course when we're using function notation we don't normally see y. Remember, the f of x represents y. So this is the f of x axis, but of course we think of that as the y-axis. So we have the graph of f here. Now, as we go through here, I want you to recall when we see the notation. Okay, let's keep this in mind, and I'm going to just make a little note down here. F of 2. Now, just as an example, I just pulled that out of the air. F of 2 represents the value of y when x is equal to 2. So let's keep that in mind as the questions are asked here. So the very first question that we're going to be asked about in this case is, what is the domain of f? Now we don't have a formula. Okay, we don't have a formula here. So we're going to assume that we're looking at the entire graph. So this graph isn't continuing up or down. We're looking at the entire graph. And so to determine the domain, we need to look to the very left of the graph and the very right of the graph. The very left of the graph will tell us the smallest x. Remember what the domain is x values. See, that's what we've got to worry about. What x values are used to create this graph, are being utilized in the graph. And so we look on the very left of the graph, and that's this position right here, isn't it? Okay, well, what x does that represent? That x represents an x value of -2. We look below on the x-axis. And so we know that x is, and because that dot is there, we know that that point is on the graph, so we have an x value of -2. Then, and every x value between -2 and the right edge of the graph, which is right there, and the x value associated with that is a 6. That's hard to see, but it's a 6. And so as we look at the graph and we think, okay, well, what about this particular x value? Does it have a place on the graph? Well, sure it does, right there. Okay, it has a place on the graph. Well, I'm not sure what y value that is, but it has a place on the graph. And so in this case, the domain is the set of all x's that are bigger than or equal to -2, because -2 x value is being used, but less than or equal to +6. So if we were writing that in set builder notation, it would be the set of all x's such that x is between -2 and +6 inclusively. It means the -2 and the +6 are both being used. So it's not very difficult. Now, if we were writing this in interval notation, okay, let's keep in mind, if we're writing this in interval notation, then the notation, then we would write that as the closed interval from -2, so the brackets around -2, all the way up to +6, and we're using +6, so the brackets around +6. Second kind of question we might be asked is, what is the range? What is the range of f? Well, the range are all of the y values used for the graph. And so now we look up along the y-axis instead of the x-axis. And we look at the lowest place on the y-axis where there's a representative position on the graph. And I'm looking at this particular y value. There's a place on the graph, and over here, and there's a second place on the graph. That's over at this point, isn't there? So the smallest y value is a -1. Okay, it represents a y value of -1. And the largest y value happens to be the y value associated with this particular point, and it's that y value which is a +3. So the y values are all going to be between a -1 and a +3. Notice I used a y there instead of an x because range are y values. Now, if we were writing this in set builder notation, we would say the set of all y's such that y is between -1 and +3. And as an interval, the interval notation would have to know we were talking about y's, but it would be from -1 to +3 inclusively, because we actually have points associated with those particular y values and everything in between. Okay, let's do this then. This next question. Let me come over here. Find f of 2. Now, what does that mean? I wrote just above this, f of 2 represents the y value, the value of y when x is 2. So what we do is we go to where x is 2. There's where x is 2. And we move to the position on the graph, and we're at this point. And so that point has what y value? Oh, that y value is 3. So f of 2 is 3. That's the y value when x is 2. Okay, let's, for what values of x is f of x equal to 0? Okay, so here's oops, that's a question mark, isn't it? Here's the idea. Remember what this f of x means. That's y is equal to 0. So what we're doing is we're going on the graph where y is 0. Well, y is 0 along the x-axis. See, along the x-axis is where y is 0. And so we look to see what points are on the x-axis. And so we're talking about this point, here, here, and here. So those all have a y value of 0. Well, what are the x values? Well, the very furthest on the left is an x value of -1. And then the middle of those points, the x value is +1. And on the furthest to the right, if we count off 1, 2, 3, 4, 5, the x value is 5. So those three x values give us a functional value of 0. That is, f of -1 is 0. See, another way to say this now is that we know f of -1 is 0. That is, when we put an x value of -1 into the function, the y value we have is 0, or that point is on the graph. Likewise, f of +1 is 0, and likewise f of 5 is 0. Okay, this question, for what values of x is f of x less than 0? So we want to look and find out what part of the graph has y values less than 0. And so when we come up here and look at our graph, to have y less than 0, it must be below the x-axis, right? For y to be less than 0. All the y's that are lower than the x-axis are negative values. all the y's that are on the x-axis are 0 values for y. And so when we're looking at the graph, we're looking along here. See, okay, right there, all that part of the graph is below the x-axis. And so those those x's, those x's are bigger than -1 and less than +1. And why did I not put equal? Because when x is -1, the y value is equal to 0, not less than 0. Now there's another part of the graph that's below the x-axis, and that's right here. Okay. Now in this case, those x values, let's see, they have to be bigger than +5, not equal to +5, because if they're equal to +5, if x is +5, the y value is actually equal to 0, not less than 0, isn't it? So we're looking for y values that are below the x-axis. Now, the largest x value, of course, is +6. But with +6, the y value is actually a negative number because that part of the graph is below the x-axis. So these are the two intervals for which f of x is less than 0. It's the two different intervals, parts of the graph. Let's look here. Let's what are the x-intercepts? Remember what the x-intercepts are? And there might be one or several. Okay. The x-intercepts are the points. Now, you'll have to be careful about your particular book or your particular homework assignment. Sometimes we list x-intercepts as points and sometimes as just numbers. But I'm going to list them as points. So the x-intercepts are the points at which the graph crosses the x-axis. And there are 3 of those points I've just circled up above. The first one has an x value of -1, but of course y is 0. So right as a point, we need an ordered pair. Not an interval, an ordered pair. A point. The second one being the point right here where it crosses the x-axis, that has an x value of +1, but of course a y value of 0. And the third place where it crosses the x-axis is at this point. And that has an x value, we decided earlier, of +5, and of course a y value of 0. So as we write them as points, we wrote them as ordered pairs. Okay. What are, and I really should say, what is the y-intercept? Of course, the y-intercept is where it crosses the y-axis. And if we're dealing with a function, we can only have one single y-intercept. We might not have any, but we can't have more than one. And remind me, that's a silly statement, isn't it, to explain to you why you can't have more than one y-intercept if you're dealing with a function. Okay. Anyway, in this case, we're looking for where it crosses the y-axis, and that's the point I'm circling right there. And so that point, of course, is on the y-axis, and it has an x value of 0 because it's on the y-axis, but the y value is -1. And so, and that's a good example of why we write as points, because if someone said, what are the intercepts, and we just said -1, are we talking about an x-intercept or a y-intercept? And here we actually have -1, 0 as an x-intercept. They're two different points, aren't they? And so this indicates that we actually have two different points. But I reminded myself to explain why a function can have at most one y-intercept. Now, it's possible to have many x-intercepts. Many x-intercepts are possible. Okay. But at most one y-intercept. Okay. So let me just draw a real quick sketch here. And let's just suppose this is where y is what, 1, 2, 3, 4, okay? And let's suppose this is where y is 2. And suppose we have a graph that comes through here and it goes through that point and does some other stuff, and then it comes back around and goes through this point, okay? And I guess we'll say, of course, that's where 3 is. Maybe that's what our graph looks like. Now here's the problem. Look at when x is equal to 0. See, when x is equal to 0, there are 3 different y values, aren't there? There's a y value of 2, there's a y value of 3, and a y value of 4. And that's the problem. Remember, whatever this function is, let's just say we call this function f, then what we're saying is f of 0 is sometimes a 2, sometimes a 3, sometimes a 4. And that can't be a function. Remember, in a function, given 1x, there's exactly and only one value of y. And so there's no way we can have a graph cross the y-axis more than one time if we have a function, because that would mean for the x value of 0, we have multiple y's associated with it. Now, that actually comes up and makes me think about what's called the vertical line test. Okay, the vertical line test. Well, the vertical line test is a graphical way, a graphical method of determining whether a graph is that of a function. And I've made a kind of a big mess of this the way I've written it out. Vertical line test. Well, it's very closely related to what we just did above. If we have a graph, okay, and let's make it a simple graph here. We have a graph that does something like this, okay. Now, the vertical line test says, okay, imagine drawing a vertical line anywhere on the coordinate plane. Well, this vertical line doesn't cross the graph at all, does it? But if we look at a vertical line right here, and suppose this is the x value of c. Let's just say c. I don't know what else to call it because I don't have it labeled. So it's some value. Now, when we look at the vertical line through the x value of c, there are 2 places on the graph that correspond to that vertical line. In other words, that vertical line crosses the graph twice. Well, then that means, that point's on the graph, and that point has an x value of c, and since I have nothing else to call, I'm going to call it a y value, y sub 2, to represent a y value. Now, on the other hand, this point also has an x value of c, but a different y value because it's lower. I'll call that y subscript 1. And if this is the graph of f, then that would say f of c is equal to y sub 2, but also f of c is equal to y sub 1. In other words, that one x value has 2 different y's associated with it. So this fails the vertical line test. Now, failing the vertical line test means a couple of things. To fail it, it means there's at least one vertical line that crosses the graph more than one time, 2 or more times. And if a graph fails the vertical line test, then it is not the graph of a function. So if it fails, that is, if there's one vertical line or several vertical lines, but if there's at least one vertical line that crosses the graph more than one time, then we're looking at the graph of something that is not a function. On the other hand, if we look at a graph, say, that looks like this, and we imagine any vertical lines that we can come up with here, and every vertical line we look at crosses the graph only one time, this passes. This passes the vertical line test. And if it passes the vertical, and what does it mean to pass the vertical line test? It means there are no vertical lines that cross more than one time. Every vertical line crosses either no times or at most one time. And if it passes the vertical line test, then it's the graph as a function. This is the graph of a function. So it's very closely related to having at most one Y-intercept if we are talking about a function. Okay, a couple more problems, or a couple more notes and another problem. Let me make a note here. Let's go to the next page. In that first graph that we looked at, that we were answering all the questions about, and I'm just roughing this in here. We had a graph that looks something like this, didn't we? Okay. Now, what I want to really discuss is the fact that this graph is ending. Okay, that it has those dots on the end are telling us a lot about that graph. So let me, and we already did the domain. Okay, in this case, I think we determined the domain. This is where -2 was. And this was actually out here where +6 is. And so we said the domain was the interval from -2 to +6. And in set builder notation, we wrote it as the set of all x's so that x was between but including the -2 and the +6. And that's the way we wrote that. Now let's look at another graph. And I'm going to make this one maybe even a little simpler. Okay. Let's suppose this is where -2 is, and let's suppose this is where 5 is, okay? And in this case, I'm going to draw a graph that looks like this. And notice I have an open dot up here. Now that open dot indicates, and that's the whole graph. That open dot indicates that that position is not really on the graph. And so if we were needing to name the domain here, at -2, we don't really have. See, at this value of -2, that point is not really on the graph. And so our domain does not include -2, but it's right up next to it, isn't it? And it includes +5 because we have a position on the graph. And so our interval would look a little strange. It would be open. We call that parenthesis open, meaning that value -2 is not included. But the value +5 is included. That's closed since it's included. So this is half open, half closed, we say. And if we were writing this in set builder notation, it would be the set of all x's such that x is greater than, not greater than or equal to -2, but less than and it can be equal to 5 because that point where x is 5 is actually on the graph. Now, we could also have something that looked like this. Okay, and I'll make this -2 again. And suppose we have a graph, maybe it does something that looks kind of like this. And now we actually have an arrowhead on one end. Okay, well, now arrowhead is telling us that we're not seeing the whole graph. It continues, and we assume that it's continuing forever. Well, here the domain, we have a smallest x value, don't we? And that point is closed in, so that means that x value is actually being used. So our x can be -2, and it can be any number bigger than -2 because it doesn't end on the right side. And so we would say from -2, including -2, to infinity. And of course, if we were writing that in set builder notation, that would be the set of all x's such that x is greater than or equal to -2. And then there are, of course, other variations of these same things that I'm indicating here. it's important to recognize that closed dots mean that's where the graph starts or ends. It doesn't go beyond that position. And an open dot means that particular point's not included in the graph at all. So that X value is not part of the domain. And of course, now you can see why we do put arrowheads, because if we don't put an arrowhead, we don't know whether the graph is stopped or it's continuing. So the arrowhead ends up being pretty important to us. Okay, let's suppose we're given the function f of x is equal to negative 3x squared plus 5x. And from that function, from that formula only, we don't see the graph, determine the following. And the very first thing, you see I left out a part of the sentence, is the point 1, 2 on the graph of f of x. Now, remember, when we're talking about 1, 2, this is a x value, okay? And we're not really seeing y's. We've, in the past, thought of that as a y value, but remember what this is. This is the y, this is supposed to be the y value when we put the x value into the function. So the question ends up being, okay, is it true that f of 1 actually gives us a 2? See, because that's for that point to be on the graph means when we use an x value of 1, we get a y value of 2. And so how will we determine that? Well, we use the function to do the work. Let's use the function. F of 1 is equal to negative 3 times our 1 squared plus 5 times our 1. And when we do this calculation, we see that we get a y value of 2. So the answer is yes, 1, 2 is on the graph. Okay. Okay, B part. If x is equal to negative 2, what is f of x? Well, this is almost too simple, isn't it? Okay. And so all this is really asking us to do is to calculate f of negative 2. That's really all it's asking us to do. So in this case, we would substitute a negative 2 in for our x value. So we'd have negative 3 times our x value squared, and our x value is negative 2, plus 5 times our x value, and our x value is negative 2. Well, when we square negative 2, we get a positive 4. And so we have a negative 3 times a positive 4, which is negative 12. And then we have plus a 5 times a negative 2, which is a negative 10. So negative 12 plus negative 10 is negative 22. So when x is negative 2, f of negative 2 is negative 22. In other words, the point negative 2, negative 22 is on the graph. I didn't ask us for that, but that's the information we just determined, really. Okay, C. If f of x is equal to negative 2, now this is different. What is x equal to? So this is really saying if y is negative 2, what is x? So that's really what it's saying in a roundabout way. Well, here's what we know. Let's come up here and what we're given. Remember, I'm just rewriting what we're given in the very beginning. F of x is negative 3x squared plus 5x. Now we're told f of x is negative 2. So that means on this side we really have a negative 2. And what we're trying to decide is what x's make that left side a negative 2, which means we're just solving an equation. So what I'm going to do is I'm going to add a 3x squared and subtract a 5x on both sides. So I'll end up with a 3x squared minus a 5x minus a 2 equals 0. And I just need to solve that equation. Okay, well, let's see if we can solve that equation. I'm going to attempt to factor this side. Let's see. Let's see if we can factor. Of course, it's going to be equal 0, isn't it? How about a 3x times an x? We have a minus 2 at the end, and so our signs are going to have to be different. And I'm thinking we need a plus here and a minus here. And we're going to have to multiply to give 2. And so I think we need a 1 times 2. If I put the 2 here and the 1 here, then aren't I going to have a negative 6x plus a 1x, which is going to give a negative 5x? Yeah, I believe we've got it factored. Okay, now to solve that equation, of course, we take each of those two factors and set to 0 and get our solutions to each of the new equations. And of course here we would subtract a 1 on both sides first, and then we divide on both sides by 3, so we get x is negative 1/3. Over here we just add 2 to both sides. And so if f of x is negative 2, then x is negative 1/3 and or, okay, a positive 2. There's two different x values that give us an f of x, a y value of negative 2. Now that's different than 1x giving 2 y's. This is two different x's giving the same y, but we don't have the same x giving 2 y's. So be careful and don't misinterpret this as not being a function. In other words, here's what this tells us, that if we put negative 1/3 into the function, we're going to get a negative 2. And if we put a positive 2 into the function, we're going to get a negative 2 out. You could verify that now by just doing your calculation. You can put those into the function. Okay, on the next page, I want to find intercepts, okay? Now, I know we're on a new page, so I'm going to rewrite the function. The function is f of x is equal to negative 3x squared plus 5x. Now, the next part of this question, D part, is to list the x-intercepts. Now, I make a habit of writing the x-intercepts as points. And that's, you just have to pay attention to the way a question is asked. Sometimes you list it as a number, sometimes as points, but I have the habit of listing them as points all the time. So let me remind you about x-intercepts generally, okay? Not for this particular one, but generally. An x-intercept is where the graph crosses the x-axis. Okay, and so on a function we can have several x-intercepts, and each of these x-intercepts we can't really look at this graph and know what the x value is, but we know because it's on the x-axis, we know the y value is 0. Each one of these, we don't know the particular x value here. We do know the y value is 0. Here again, we don't know the particular x value, but we know the y value is 0. And that's the giveaway about how we find x-intercepts. So to have an x-intercept, the y value must be equal to 0. That's the only way we can have an x-intercept. And so when we're finding x-intercepts, we just go to we go above, f of x equal negative 3x squared plus 5x. Well, this is the y value, isn't it? And so we end up solving the equation, replacing that f of x with a 0, and solving the resulting equation. So finding x-intercepts always requires solving equations. Now, in this particular case, I notice on the right side I have a common factor of x. And so I can factor that common factor of x out. and I would have something that looked like this. Now to solve this equation, then I would take each of the factors, x is one of them, and set it to 0, and take the other factor, negative 3x plus 5, and set it to 0. And so in this case, I already have one solution, that's x equals 0. To get the other solution, I continue solving here by subtracting 5 on both sides, and then dividing on both sides by a negative 3, and so I get x as a positive 5/3. And we'll leave it as a fraction. We won't use a calculator and approximate that or write it as a decimal. We'll leave it exact, just as I have. So those are the two x values. So if I'm listing the x-intercept, one of them has an x value of 0, and of course they both have a y value of 0. So the next one has an x value of 5/3, but of course an x-intercept always has a y value of 0. So those are the two x-intercepts. Okay. List the y-intercepts. Now let me remind you, this graph up above, this graph up above, that wasn't the graph of our function. That was just an illustration about what we know about x-intercepts. Now remember, we have a function here. And so we can't have more than one y-intercept. So it's silly to say list the y-intercepts. There will only be one. And once again, I'm in a habit of writing my intercepts as points. But let me remind you for a graph in general. A y-intercept is where we cross the y-axis. And whenever we cross the y-axis, what we know about that point is the x value is 0. But we don't know the y value, and that's what we're really trying to find. And so the secret then is that when we're looking for y-intercepts, we let the x value be 0, because it has to be. And so we go to our function to calculate the y. And remember, the y is the value we get when we put the x value of 0 into the function. So we just put 0 into the function. So we have negative 3 times 0 squared plus 5 times 0, and that ends up giving us a 0. And so there is only, so the y-intercept has an x value of 0, as always the case, but in this case the y value is also 0. And now, of course, that matches an x-intercept up above, and yes, of course, if we would have noticed that, 0, 0 is the origin, and that is an x-intercept and a y-intercept because it's on both axes, isn't it? But that's how we would have done this generally. Well, that's the end of what I had to say about interpreting and reading the graph of a function. A good look on your homework.